Dr. Jamil Saeed. Dr. Saeed is currently working with the Canadian federal government, where he specializes in the evaluation of public policies, particularly labor market interventions. His work involves applying advanced causal inference and machine learning techniques to assess program effectiveness and inform evidence-based policymaking. This lecture will provide a valuable introduction to modern causal machine learning methods that combine the strengths of traditional econometric identification strategies with flexible data-driven algorithms. As these tools are becoming increasingly prominent in applied economic research, impact evaluation, and policy analysis, this session will be especially relevant for individuals interested in program evaluation, development economics, labor economics, and related fields. We are honored to have with us Dr. Deen Islam as our moderator. Dr. Islam is a research director at Rapid and associate professor at the Department of Economics in the University of Dhaka. So now, without further ado, I would like to hand it over to Deen sir to moderate the session. Thank you so much for joining us, and I hope that this session will be very fruitful and a great learning experience for all of you. Thank you. Over to you, Deen sir.
Thank you so much, Jana, for a nice introduction. I would like to thank Dr. Jamil Said for agreeing to deliver this very interesting lecture. So, students, researchers, everyone, I think, will be benefited from this lecture. And those who are interested in working in machine learning, especially the causal machine learning, this lecture will be very helpful. So, before I go to Dr. Jamil Said for his lecture, let me now request our Executive Director, Dr. Abu Yusuf sir. Sir, if you can say a few words about our today's special lecture.
Thank you, Dr. Din Islam, Dr. Jamil Said. Welcome to Rapid webinar series. I think it's our every month. This is our regular webinar that we organize, but sometimes we organize the policy competition also. But this time, I think this is a new edition with your lecture. So, Dr. Jamil Said, who is working for the federal government of Canada, and I think a very interesting topic, as indicated by Dr. Din Islam, that causal machine learning methods, very modern, technique, and also contemporary issues. So, hope through this lecture, our audience, our young researcher, through social media, and also those who join directly with this webinar, they will be enormously benefited. I'm really grateful to Dr. Jamil Said. Hope this is the beginning of our interaction. We will be interacting in future as well, and through your expertise. I think this is also a contribution of your contribution to our country, to our young researchers. So thank you, Dr. Jamil Said, and thanks to Zara, Dr. Din Islam, and Shahidul Islam for organizing such a wonderful webinar. Thank you.
Thank you so much, Yusuf sir, for your encouraging words. So, as Yusuf sir was saying that we are trying to bring some new issues, new topics, so that the young researcher will be benefited. So, without further ado, let me now request Dr. Jamil Said to deliver his special lecture in next 40 minutes. So, we will not take questions during the presentation. Please note down any questions, anything, and we'll open the floor after his presentation. But if you have any very emergency clarifying question, you can raise your hand, and in that case, you will be allowed to ask Dr. Jamil Said. But otherwise, we'll first hear his lecture, and then we'll open the floor for question and answer. Okay, Dr. Jamil Said, if you kindly take next 40 minutes to deliver your lecture.
Assalamu alaikum, everyone. Thank you so much, Dr. Dean. He's a good friend of mine for organizing this event. Really grateful to be here, and it's a great opportunity for me to also present this kind of emerging topic in economics and also data science. I will share my screen and then we can move on. So let me know if you can see my
Yes,
screen.
yeah, we
You can
can
see the
see.
slides now?
Yeah, it would be better if you can. Okay, yes, yes, we can
Full
see it.
screen now. Yeah. Okay. Perfect. So just to introduce me quickly, I actually work in federal government of Canada as a program evaluator. So my main task is to evaluate social and labor market programs. And today's talk is related to mainly the labor market program. However, the implication of this topic can be extended to other fields. So in Canada, basically, if you know about the labor market here, so we have two layer of I would say kind of support for those who becomes unemployed. So at the first level, what happens is that they are given unemployment benefits. And then in the second level, what happens is if someone is interested to take some training to develop their skills, then they are provided those kind of training. So as the evaluator, our task is to kind of evaluate how impactful these training programs are. And over the time, I think for last 20 years, the main method that we have been using was matching method, sometimes combined with difference and differences. And as you know, these are the very classical, and also we call it like traditional approaches, very well-established approaches to assess the labor market impacts. Not only labor market, it's any kind of impact analysis. These methods are really robust. But in recent days, probably in last few years, there is a new field developing, which is the causal machine learning. And this causal machine learning has a great prospect because it has some leverage and it has some special, I should say, some tools with which it can really allow us to look deep into the impact analysis. So today's my discussion would be in two parts. So in the first part, I'm going to explain the impact analysis based on traditional approach. What I mean by that is the matching method and the difference in differences, which actually we use in federal government, and then we will move to the causal machine learning, some basic ideas. Especially, I'm going to talk about the approach that we use in the government, which is the modified causal forest. It's a very innovative and very recent development. So we are still working on this, and this method, I will show the basic idea about this method and how we can implement this. So the second part would be a kind of more of a, I would say it's kind of a practical illustration where I'm going to show like the 10 steps that we define to implement this causal machine learning. And also I'm going to show you some results using a synthetic data. So before I begin, again, there's just a quick disclaimer that all the materials and on the information that I'm going to discuss is solely from my own side, and I'm not representing the federal government here. Um, so again, this is again for the dissemination purpose. So let's jump into the main discussion. So first, I will give you a quick context. So what I'm going to discuss. So when we talk about impact analysis about any program, especially the labor market programs, we know that there is a fundamental problem in the causal inference that we have to face. So the challenge is that when we are talking about an intervention, so there is a participant and there's a control group. And what happens is that we cannot or can never actually observe the outcomes of the same individual in the two states. So what I mean by that, so think about individual who is participating in a labor market program, so this kind of training program. So what we can observe is that he takes the training, and then after taking the training, we can observe his outcomes, for example, earnings after a few years. However, we cannot actually see what would have happened if that same individual did not participate in the program. What would be his outcome, his earnings, and if we consider the same time period. So this is this problem in causal inference, as we know that this is solved using a potential outcome framework. And what do I mean by that is basically that the fact that we cannot observe the causal effect for an individual, what we can do instead is to take the average outcome of the participant and then take the difference of the non-participant outcome from that. This will give us the causal effect. However, there are some certain conditions, some assumptions that needs to be fulfilled. So I will discuss those in a moment. And as you know, in this kind of observational setup, we usually use a non-experimental design. What it means is that we have the participant group, but we have to create a comparison group. And from that comparison group, we will construct a counterfactuals. So basically, this is for every individual, we will have his counterpart who is not participating in the program. And then we can estimate the treatment effect for that program. And as I said before, that the well-established method that in most of the studies we use for non-experimental design is the matching methods, and sometimes combined with difference in differences. And we are calling this traditional method. So now let's look at the concept of treatment effect heterogeneity. So we talk about the average effect of the program, right? However, if we think about like a group of people who are taking part in the program, it's quite obvious that not everyone is going to be affected in the same way. Some of them is going to be affected better than the others, right? Some of them would be better off, some of them would be worse off. So this kind of variation in the treatment effect is known as treatment effect heterogeneity. And the traditional methods are not optimized actually to identify this kind of treatment effect heterogeneity. So now comes the causal machine learning, where this actually gives us a way to identify these kind of treatment effects and also estimate these effects. So for those who are familiar with traditional machine learning, you know that this machine learning is basically is very good at prediction problem. So what happens is that the new branch, which is the causal machine learning, is a blend of traditional machine learning as well as the causal inference, right? So when we talk about causal inference, it's basically some of the conditions that needs to be fulfilled to estimate the causal effect, right? And as we said, the traditional machine learning is basically is a kind of tool which optimizes predictive analysis, right? So we are kind of combining these two, and then we have the causal machine learning. And within causal machine learning, there are two main, approaches. One is the double machine learning, and the other one is the causal forest. So today we are going to focus on the causal forest approach, which is kind of a tree-based approach. If you are familiar with random forest, this is a tree-based approach. So Causal forest is kind of is a framework built on that random forest framework. And more specifically, I'm going to talk about the modified causal forest, which is an extension of the causal forest. And the causal forest, I need to mention that this was mainly introduced by Wager and Athi in 2018, and then Michael Lechner, he kind of extended this approach, and that's known as modified causal forest. So, what is the best part of modified causal forest? What is the best thing it can do? So, modified causal forest, the greatest advantage that it has is that it can identify the treatment effect heterogeneity. What it means is that if we can know that who is getting benefited and who's worse off from participating, then basically for as a policymaker, it's good for us to better understand how the program works and to probably redesign the program. So basically what we say, what works for whom. So basically the policy question is what works for whom. Okay, so in this very simple infographic, you can see that we have a labor market program where we can see there are four types of people, right? Or basically, I should say three types of people, and then we will have an average. So three types, if you look at the green, is basically who are getting benefited from the program. The blue is someone is neither benefited nor worse off. And the red one is someone is kind of worse off from participation. So with traditional method, if we are estimating the average treatment effect, so we are getting some like an individual, I mean, we are getting a causal impact, which is giving us an overall impact. However, we don't know exactly who is benefited, who is worse off, right? Whereas in the heterogeneous treatment effect, if we can identify this, then we can get an estimate for each of the subgroups. So we are calling them subgroups, right? So there will be one subgroup who is benefited, one of them is neither benefited nor worse off, and then another one is kind of worse off. So before I jump into the causal machine learning, I will quickly go through the very basic idea about matching methods. So as you know, in matching methods to estimate impact analysis, we basically have two groups. We have a participant, which is the green one here, and the comparison group, which is the blue one. So in the data, we have different types of individual. We have both groups, but in terms of social demographic characteristics, they might be different, right? So matching method, what it does is it tries to um, kind of match one individual with his closest counterpart, right? You can see here that kind of scenario. And then obviously at the end, there will be some people who are unmatched as participants, and there will be some people in the control group who are unmatched in the non-participant group, and then we have to exclude them. And then once we have this kind of, participant group and comparison group, these two groups, we'll ensure that they are very similar in terms of characteristics. And then the matching is done basically, we can do it in propensity, based on propensity score. And also you can use kernel matching. So again, these things are, I think many of you are familiar with. So just kind of an overview, what we do in matching. And then in the second step, if you want to estimate the impacts of the program, you can combine with difference in differences. And the good thing about differences is that you can control the unobservable factors even here, as long as they are stable over time, right? So as we know that in difference, what happens is like we have a panel data and we know the information before and after participation. I'm talking about the outcomes. So what happens is we basically get the differences of outcome before and after for participant, and then we have the differences in outcome for before and after for the comparison group, and then we take the difference of that will give us basically the average impact of the program. Okay, so let's talk about the causal forest, very basic concepts that we have before we move into modified causal forest. So in traditional machine learning, as I said, like it's very it is optimized for predictive analysis, and random forest is the tree-based approach that we usually used in the literature. So this random forest framework can be transformed to causal forest based on the fact that we satisfy the classical identification assumptions for causal inference, as well as there are some changes in the algorithm, that there's change in the setup for the machine learning. So again, the classical assumptions, many of us are aware of this. Still, I just quickly go through this. So there are mainly four classical assumptions that we need to satisfy for causal inference. One is the conditional independence assumptions, or CIA. So this basically says that if you have the feature or the control variables in your model, these covariates, you have to ensure that they do not jointly influence your treatment and the potential outcome, right? So this is the assumption we need to satisfy. Second one is the common support, which kind of an assumption which ensures that there is a positive probability of being participant and non-participant given the features in your sample. And then comes the stable unit treatment value assumption. So even though the name is very big, the idea is very simple. The idea is that you cannot have different types of treatment for a group of people. The treatment would be kind of same treatment should be given to everyone. And the second thing is that there is no spillover effect from the treatment, right? So someone's outcome cannot be affected by someone else treatment assignment. And the last one is exogeneity of confounders. So basically, this means that your treatment status do not influence your behavior. So as long as these assumptions are fulfilled, then we go to the next step and do some changes in algorithm. So I'm talking about very, very basic things. So first one, we are talking about the sample splitting. So if you know, in random forest, the tradition is to take two splits of the data. So if I have a data, I would split it into two parts. 80% would be training and 20% would be my test. Whereas in causal forest, this splitting is done in two parts, but equal. So I will have training set as before, like 50%, but the other 50% is known as honest set. So why it's called honest set? Basically, with half of the data, we will build the tree, or we will build the model. So we will kind of ensure that where would be the splits of the tree, and the other half of the data, we will kind of run the model again and do the estimation of the treatment effect in the leaf. So I will show you in the next slide what it means with a simple diagram. But the other part, which is the objective function. So as we know that in random forest, the objective is to do the prediction. So what we do is the main objective is to minimize the prediction error. We call it mean square error. And where in this case, in causal effect, it's a little bit different, because now we are talking about causal. No, you are not talking about prediction. We're talking about causal effect. So what we are going to do is to maximize the heterogeneity in treatment effects. That means we have different splits and we have different leaves. So we want to make sure that in different leaves, there are different types of people. So the causal effect will be different. So this is one of the objective of our main model. And also, we want to minimize the heterogeneity in the treatment effect. That means in one group, in one leaf, we have kind of similar people. So making them more homogeneous. So I know, this might be a little overwhelming to digest, but if I can explain this with a simple diagram, I think it will be much better. So think about, I'm just looking at one of the trees in the forest, right? So when we talk about causal forest, there are many, many trees in that forest. We just look at one tree, and this is only for illustration. Obviously, even the one tree is very complex. There will be many, many branches based on how many features I have, how many covariates I have. So I'm just thinking about a very simple tree where I have first of all, first thing to see here, I have two main groups. So you look at the stars. This star means participant, and someone without the star is non-participant. And the second thing is there are four subgroups, four types of people. So one is you see the green, and then you have red like that. Now, what happens that if this is my whole sample? If this is my whole sample, then how I make the tree and how I estimate the causal effect. So I have three features. So gender is one feature, male, female is the category. And then you have education, and then you have age in the other side, right? So this node, we call it node, this is called the root node. So this is the start of the tree. From the root, if I put gender, then I split in this way, and then in this new, this is called child node. So here in the child node, I'm splitting again the data based on education. So here, based on education, I can split into two subgroups. And finally, if I stop here, this is the leaf, right? This is the final group I have. And then the other side, I'm splitting based on age, and this is the final two leaf. So you see in the final leaves, there are four subgroups. And then in each of those groups, each of this leaf, I have two groups. So one is the participant, and one is the non-participant, right? So if I take the difference, that would be my treatment effect. And you see, finally, the treatment effects is not same for everyone. So you can see someone is getting benefited, highly benefited, someone is like mediocre, and then there's some of people who are kind of worse off from this participation. Okay, so next, just to simply understand some of the parameters or estimates that we need to know about causal forest. So first one, as I said, that the best part of using causal forest or causal machine learning is that you can estimate the treatment effect at different levels of granularity, right? So I can be at the fine grain level of treatment effect, which we calls as individualized average treatment effect. So this is the bottom where I can go, right? And this depends on, obviously, how far I can go depends on how many features I'm, right? The more features I have, I can go to the smallest subgroup possible, right? Um, and then if I have that, what I can do is I can aggregate those treatment effects and go to a group average treatment effect. So what is a group average treatment effect? This is basically is a group which is kind of meaningful for the policymakers. For example, I can make group based on gender. I can make groups based on nationality, right? So this is the group, because this is very disaggregated and hard to analyze. But this group average treatment effect is something which is easy to explain to the policymakers. And then finally, if I even aggregate these group effects, I can go to the average treatment effects, which is the population average, and which is also can be done with traditional approaches. So here the advantage is in machine learning is to get this IAT and this gate. Now, what is modified causal forest? This is an extension of the causal forest, as I said, and based on two main modifications. So first modification is that for the sample splitting, there's a new rule introduced which basically tries to reduce the selection bias, because we know in observational studies we always have selection bias. So the splitting rules kind of try to address this. And the second modification is that once we get the estimate, obviously we need to do the inference, like we need to see whether it's statistically significant or not. And this modification basically is done based on a weight approach. So this weighting approach inference, this helps us to basically look at this inference at different levels of treatment effects. And it's also helpful to interpret the results. Now, finally, what is the biggest advantage of this MCF approach over the traditional approach? So one is very straightforward, which is that in traditional approach like matching, these are the semi-parametric methods, whereas machine learning is mostly non-parametric, and that's why they are very flexible. So you don't have to kind of assume a functional form to do this kind of analysis. And second one is most important. This one says that when you are doing traditional approach, I can do the subgroup analysis in the sense that they would be kind of done separately. So, for example, I have male and female, so I can estimate the treatment effect of male, and also I can estimate the treatment effect of female, but I cannot compare them. I cannot compare the treatment effects of male and female because they are not done jointly, right? The treatment effect assessment is not done jointly. Whereas when you're doing MCF, these estimations are joint estimations. So at the end, once you get the gate, the group average treatment effects of male and female, for example, then I can compare which one is larger, who has a higher benefit from the program participation. Okay, now we're done with the first part of the discussion. The second part is basically about the framework. So if I have a data, how I can work on causal machine learning, how I can implement. So what I'm going to do is I'm going to quickly explain a case study. This is a synthetic data, artificial data, and then I will show some steps, and as well as I will show some results, how we will get. So quickly on this case study, we have about a short-term training program on skills development. So some people comes to the program for 3 to 6 months, they get a training, and then this training, after getting this training, we will see what is the impact on their outcome, which is the earning. And this program basically starts in the first quarter of 1993. Age group is 30 to 50. And also we have a large number of socio-demographic and labor market outcomes, as well as features of the participants. And also we have a comparison group. A comparison group means here those individuals who are eligible to participate, but they did not participate, but they have the same kind of or not same, I would say similar kind of socio-demographic characteristics. Okay, so what is the first step we should do? So once we have a data, once we have a research question, or I should say, once we have a project to deal with, so I have to understand what is the setup of this study, and what is the question, what is the we sometimes, most of the time, call evaluation questions. So because we are evaluating the programs. So here, as you from the case study, this is basically an observational study, right, based on labor market program, and we are using administrative data on short duration skills development program, right? And what is the objective? The objective is to estimate the average treatment effect, but most importantly, we want to detect and estimate the heterogeneous treatment effect of the training program. And we're talking about medium term outcome because your outcome can be immediate, like 1 or 2 of year after participation. It can be 5, 6 years, or it can be long term, right? So we're talking about medium term, and we're going to use causal machine learning. Second step, we need to understand what is the model here we have. So, and when we talk about causal model, so specifically in impact analysis, we are talking about treatment and outcome, which is the basic two, variables. So treatment is obviously the labor market program, and outcome, we are defining it as a medium-term outcome on earnings. So it's a fourth quarter of sixth year of post participation. And again, as I said, like there is a lot of socio-demographic variables for this case study. And that's why the model is basically selection on observables. So basically, it means that we can model based on observable factors, right? Because we have a lot of information already, and we can control those confounding factors. Now, the identification assumptions that we already talked about, the 4 of them. So quickly on those, we have to justify why these assumptions actually hold. So most of the time, it's kind of a justification rather than you can test it, right? A few of them, or one of them you can test, which is the common support, which I showed here. So this common support is kind of is plotted for the raw data, and you can see the treatment is the blue, right? And the other one is the control. So there is a good overlap of treatment and control, which is kind of unusual in the real life data. Because this is the synthetic data, we can actually make the data in such a way that we ensure that there's a good overlap. So the treatment and the control, they have similar characteristics. This is what I mean by good overlap. But in real life, you might not have this kind of scenario, right? And then, as I said already, the CIA is holding because we have a large number of data, and the SUTVA, this is no spillover from the program. This is, you can justify saying that the program is small compared to the labor market, right? So there's no chance of spillover. And finally, the exogeneity of confounders means your treatment effect do not influence your behavior in the sense that here we can justify because the participant actually came to know about participation decision in the same quarter they participate. So there is not enough time to actually change your behavior. Okay. Uh, so next one, let's go to the data processing. The standard ones, we know we just need to remove missing values, check for duplicates. You can do some variable transformation, everything that you need to do to create the final file. And then also you need to create the comparison group at the same time, which are the eligible non-participants, and ensure that they have the same kind of information as the participant. And also you need to have a sufficiently large comparison group. For this study, we have two comparison group individuals for one participant. Okay, so now once we have the data ready, then we can do some pre-estimation diagnosis. So one of the very standard one is the outcome trend analysis. So this is not a causal analysis, this is just a descriptive analysis. So what we can do is we take these two groups, plot the earnings like before and after participation. So you can see here that the green line is basically the non-participant and the orange is the participant, and then you see there is kind of a flat portion. So this is the time of participation. Participation starts, right? So because this is like 3 to 6 months, so first 2 quarter you see there's no income for the participants, and this is what we call lock-in effect. So lock-in effect means that you do not earn because you are actually engaged in kind of skills development training, right? And then you see even the outcome trend showing that the participants have a higher earning compared to the comparison group after like 6 years. However, we cannot make any kind of causal inference from here. So what we need to do is go to the machine learning. We run the code. The MCF algorithm, what it will give us, first, the most granular level of treatment effect, right? And as I mentioned, this is known as IAT. So once you get the IAT, what you can do is basically aggregate and then go to the more aggregate estimators. For example, we can go to the gates, you can go to the ATE, right? So we have two estimates in aggregate for the average, so which is ATE, average treatment effect, and then you have ATT, so average treatment effect for the treated. So what's the difference? So difference is that the ATT is basically shows the treatment effect for the participant, and this ATE shows the treatment effect for overall population. So we also consider the comparison group. So to be in very briefly how it's done. So when we are calculating ATE, we look at the comparison group, right? And also we think about a counterfactual for the comparison group. That means for every individuals who did not participate, we have to create a group of counterfactuals which will show what would happen to those non-participants if they have participated, right? So, and then we estimate their the treatment effect also. So you see the average impacts, both are statistically significant. However, we will mainly focus on the average treatment effect of the treated for rest of the analysis. Main reason is that when we are doing program evaluation, our main concern is with the participants. Even after doing the net impact analysis or this kind of impact analysis, what we do is kind of a cost benefit analysis, right? So we see whether the program is cost effective, right? So we look at the cost of the program, benefit of the program, and then we compare, right? So this kind of analysis, we need the treatment effect for the treated, right? We cannot use the overall population. Okay, now this is the most interesting parts we will start. Uh, I know I'm probably a little bit running late with the timeline, but I will try to keep up. Okay, so first, identifying heterogeneity at individual level. As I said, like we first identify the individualized treatment effect. So we can do, there are two approaches to identify the heterogeneity. What do I mean by heterogeneity here? Again, to clarify that I want to see that these treatment effects, are they different, significantly different for different peoples, right? So one thing we can do is just to simply plot them and then see, one is this line, this reference line is 0. So this means that there is someone here who is neither benefited nor worse off. Well, I mean, he's so in not in either group, so he's kind of a neutral one, right? So in that case, everyone to the right, these are all benefited group, right? And everyone to the left, they have negative treatment effect. That means they're worse off participation. And here we estimated like 83% of the participants are actually having positive treatment effects. So they're better off, and 17% are worse off, right? So even though the average treatment effect, if you go back, you'll see is for the treated is 662, but you see that there are individuals who have positive benefit, who have negative benefit, right? So this is kind of heterogeneity. Second way of identifying heterogeneity is to plot the difference between the individualized treatment effect and the average. So this line is basically the difference. It's not the IAT. This is the difference between IAT and the ATE, right? So how can I understand whether there is heterogeneity? There is a reference line which is 0, right? And you will see that those who have negative treatment effect, here these people in the left side of the graph, and then the right side, these are those who are benefited from the treatment, right? And there is a gap between 0 and this confidence interval. So as long as there is a gap, that means the treatment effect of these individuals are statistically significant, significantly different than the average. And also we have some people here. So there is evidence of treatment effect heterogeneity. Now, in terms of group effect heterogeneity, what I can do to identify this, first we have to estimate the gate, the group average treatment effect for the treated. And we have 4 subgroups for this analysis based on gender, age, nationality, and education level. So you can see all the estimated values, and there are some of them are more than the average, and some of the groups are less than the average. And there are 2 groups, I think, like the male subgroup and the age subgroup 30 to 40. They basically their estimates are not statistically significant. Other than that, everyone's effect is significant. But again, just to remind, this is the treatment effect for a subgroup. But how can we actually detect the heterogeneity within the subgroups? So whether the subgroups, one subgroup has statistically different treatment effect than the average. So what we need to do is similar to the individualized way. We take the difference between the gate, group average treatment effect, and from the average, right? And then we plot, and again, 0 is the reference line. So as long as the confidence interval does not cut the 0 reference line, that means it's a statistically significant difference, right? So male, female, you'll see have heterogeneity. And this subgroup is based on nationality. So again, this is kind of local, and then I think this is a non-European, and then you have other nationality. So these two are like, these two subgroups have heterogeneity, but these ones you see they are overlapping or cutting the reference line. So there is no heterogeneity for these subgroups. And same for other ones. So again, this is just for sake of time, just move on to the next part, which is the most important, I would say, of this analysis, and I will spend a little bit more time here. So once I identify the treatment effect heterogeneity, I need to explain these results. I need to interpret the findings. And the challenge of interpreting this effect heterogeneity is that I want to know where they are coming from. Are they coming from the variable of interest, or are they coming from confounding features? So I give a very simple example. So think about how we actually first do the group average treatment effect, for example, for gender, right? So I have male and female. So for male treatment effects, I have 2 groups initially, the male participant and male non-participant. And we kind of have the similar characteristics. We balance the characteristics between these two groups. So at the end, their outcome difference is mainly because of the participation, because the two groups are same in terms of features. Same goes for the female subgroup. We have female. Sorry, I think someone's microphone is not.
আর হবে না কোনো কিছু
Okay, I think if the microphone is muted.
Shahidul,
Yeah,
can you mute? Jara, Shahidul, can you mute and give it?
শহীদুল ভাই, আই থিঙ্ক ইউর দ্য হোস্ট নাও। একটু আয়শা নূর আপুকে একটু মিউট করে দেন শহীদুল ভাই। থ্যাংক ইউ।
Okay, perfect. Thank you. So
Sorry
just
about the inconvenience. Very sorry about it.
yeah, no problem, no worries. So just going back to what we were discussing. So we were discussing about the source of effect heterogeneity, and I was giving an example about male and female. So if male and female group average treatment we estimate, now I want to see whether these treatment effects between male and female, they are different, statistically different than the average. So um, as I said, like when I estimate the gate for the male, I have participant male and non-participant male, right? And then I balance their features. But now remember, I'm not comparing male participant with male non-participant. I'm comparing male gate with female gate. That means I am comparing male participant with female participant, right? Male participant and female participant. These two groups are not balanced. They are not same in terms of all the socio-demographic and labor market characteristics. They can be different. So, for example, male can be more educated than the female, for example, or male can be more experienced than the female on average in the labor market. Then at the end, I cannot compare the gait between male and female because they are not, the features are not balanced. So what we need to do is that we need to balance the features to ensure that the differences in male and female estimates are only coming from the gender itself, right? If we can ensure that the male and female group are balanced in terms of all kind of features in the data, then if there is still difference remaining in the treatment effect, then we can only say that this differences is because of the gender difference, right? So let's look at an example. I think it will be clear when we look at an example. So I take two subgroups. One is non-European subgroup from the nationality, and female participants, which is based on gender. And how I can interpret based the two ways to interpret. So for the sake of time, I'm not explaining too much about analyzing profile of subgroups because this is very basic analysis. And this is just the main thing is that you just take the profile of male and female, for example, and then we try to see on average is a male more educated than the female. On average is male more experienced than the female. So we try to find the features which actually makes them different, right? And the second is actually what I discussed now, that the group average treatment effects were not initially balanced in terms of features. So I have to balance them and then again check the heterogeneity. So what do I mean by that? So there's a new parameter that can be estimated, which is called balanced. So previously we had group average treatment effect, and now I have balanced group average treatment effect, right? So the difference is when I estimate the gate group average treatment effect, the features of the two groups were not balanced, right? For example, when I'm doing the subgroup based on gender, the male and female, their features were not the same, right? But when I'm doing the B gate balanced group treatment effect, I ensure that on average, these two groups are similar in terms of all the covariates, the features, and then I try to detect the heterogeneity. So I take the difference of B gate minus the ATT. So what is the rule of thumb? So we propose a very simple rule of thumb. So once I estimate the B gate and take the difference, if the difference still remains, I mean, it becomes statistically insignificant. So remember, if I go back just to quickly show you, here for the male female, for example, you see that they are statistically significant, the gait variables, right? But they were not balanced. But when I have the B gate, I actually balance, and if after balancing this gap is no longer statistically significant, then we can say that there is no evidence of effect heterogeneity, right? Because once I make male and female similar, if the difference is no longer exist, that means gender does not actually affect the treatment effect. On the other hand, even after balancing all the covariates, if the difference between these two, B gate and ATET, is still significant, that means there is still evidence of effect heterogeneity. Okay, now quickly with an example. So we talk about non-European and we talk about female subgroup. So for non-European, you will see first, this is the non-European column. We have the gait variable, gait minus ATET, without any balancing, right? We do not balance any variable. So estimate is 140, but it's also statistically significant. Once I balance all the covariates, I have the B gait, I see that estimate goes down. More importantly, it's not statistically significant. That means there is no evidence of effect heterogeneity. Whereas the female, you see the gait minus 80 was 566, and also the p-value was statistically significant. And then when we do the balance gait, my estimate increases, and most importantly, it remains statistically significant. That means that gender has a effect on the treatment effects. Okay, finally, the last step is the post-estimation analysis with clustering. So what we can do is we can take all the IATs, individual treatment effects, and then we can use a k-mean clustering, and then we can identify which cluster or which group is most benefited, right? So here you can see that this is, again, you don't have to do anything. You can just put the code, and then the algorithm will decide like these three groups are the unique groups. And then you can see here, based on the individual treatment effect, this is the most benefited group. And the most important thing, and this is the interesting one, that you can actually characterize who are in this most benefited group, right? So we can see in this group, you have mostly female, aged between 40 and 50. That means a little bit older in our data. They have university graduate, and also they have high labor market attachment before participation. So that's why clustering is important. Okay, so that just to conclude my this discussion. So we talk about modified causal forest algorithm, which is a extension of causal forest, in terms of its value in estimating labor market program impact. And we have seen that it has some very good advantage compared to the traditional approach. Even within the causal machine learning, this approach is considered to be one of the best to detect the effect heterogeneity. And why this is important, this effect heterogeneity, because this actually helps the policymakers to make better policy in terms of optimal targeting. And finally, this is not only for labor market. I just show an example with labor market, but this kind of approach can be extended to other fields. For example, any other social program, business decision, marketing campaigns, medical treatment, many other things. As long as you have an intervention and your main goal is to identify whether there is a differences, like significant differences in the treatment effects. So again, hopefully this was useful, and if you have any question, I'll be happy to answer. Thank you.
Thank you so much, Dr. Jamil Said. It was a very comprehensive lecture, and I think it would be a good starting point for people who are interested to use this advanced model to do some causal analysis. So let me now open the floor. If you have any question, you can write it down in the chat box, or you can raise your hand and I will allow you to unmute and ask the question. Any question, anything you would like to ask Dr. Jamil Said?
Then let me break the ice, if you would allow.
Yeah, please.
Dr. Jamil Said, it was a wonderful presentation and it was quite educational for me. And I must admit that I haven't understood much, but I have got one basic question to ask you. And if I dare to ask you that question, is that like, in normal being an economist or as the profession of the economics itself, we tend to rely on our theoretical perspectives, like, why some people would react to whatever interventions you make and what could be the impact and how those impacts could be analyzed, you see. So that's what we have been doing until now. Now, through this machine learning thing, the problem is at certain point, perhaps we are transferring that knowledge to the machine to determine and identify pattern and whatever to tell us the impact or the impact at the individual level. In that case, my question is, can you then undo your result and then try to tell us, no, those were the factors that actually affected some individual not to react to the interventions that those are made. So the question is more or less like, do you really learn anything out of these machine learning things when the machine is doing the thing? But as my theory, as my learning of economics, whether it is actually helping me to get the picture better or have the insights. I'm not sure whether I have been able to make you understand, but that's what, came to my mind. Yeah. Over to you. Thank you.
Thank you so much, Rajak sir. I think it's a very, very important question. And actually, we face this when we actually present this to even within our government. We present to other policymakers, other groups who actually run the program. Basically, with most pushback we get from those who are running the programs, right? We are kind of evaluating. We are in the back end, but they are in the front end, right? So if I understand correctly, so I would break it down into two parts. One is you are asking about like how different this might be compared to the theoretical framework and right now in machine learning. What's the difference, right? So I would say I think at the beginning I was saying that machine learning is not actually magic. It's something based on like data where we allow the data to speak. Most of the time, those who are proponent of machine learning, they say we allow the data to speak. So what does it mean? It means when we are doing traditional approaches as the matching and difference in difference, you have some flexibility in terms of defining the model, right? You have those kind of functional forms. You can say, I think this model is like this. These are the parameters you can you justify more, right? Whereas in machine learning, mostly if I talk about traditional machine learning predictive analysis, sometimes it's not convinced because we throw all the variables. We have no idea what's going on. This is a kind of a black box, right? And hard to explain after we get the results because these are kind of predictions. But I would say those are kind of a different purpose because my concern is prediction. I don't care why it's happening as long as that's the case, then it's okay, right? If I just need like, okay, what would be my prediction for GDP next year? But that's why the causal machine learning comes in as a tool which fills this gap. How this is filling the gap? First of all, this is, as I said, it's not a magic in the sense that I still need to satisfy those identification assumptions, right? That the same thing we do in matching. Like I have to ensure that this is the causal effect, right? The difference is that instead of very rigid in terms of functional forms, which can be subjective, right? Sometimes you might have a functional form, you justify, I have a different functional form, I'll just justify, right? Based on, you might be smarter than me, then you convince most of the people, right? Here we are saying that no, let's let the data work. Let data speak. We have this kind of, the tree, which will make the splits, and they will make sure that all possible kind of splits. So there is no kind of judgment, right? So it's not like one tree. I showed you one tree, but there can be like thousands of trees. So one tree will take gender at the beginning, and then the education. Another tree will take the age at the beginning and gender afterwards, right? All possible combinations, and then get the final estimates. So this is would be my answer first part. Second part, I would say like what the pushback we get is that people ask us that, okay, what is the future of this? What is the implication? So one implication is that what I explained now is that I have the existing data. I try to explain the heterogeneity, which we cannot do in traditional approach. It's hard to do, right? It's not impossible, but those like shortcomings or limitations of traditional approach, because there is no joint estimation. But because now it's joint estimation, I can compare male and female, right? The estimate. That's one thing. Second thing is that what about the future? I know about the past. I know how the program is working. Now I can go to the caseworker, right? As an evaluator, I can go to the casework. I can say, okay, I see there are some issues. You are not choosing the right people in the right program, right? Like someone is worse off participating. Now, next time you go, you should choose those people who are benefiting, right? Because I don't want to waste the money, right, on people doing and they're worse off. So there is optimal targeting. And this is another literature. So I'm also still very new for me. I'm kind of trying to study this. This is called optimal policy learning. So what we are trying to do is, if there are like multiple intervention, like 4 or 5 types of intervention, right? Like skills development, wage subsidy, and other types of intervention. And I have a group of people. Not all people are good for skills development, right? Not all people are good for wage subsidy. I want to assign the right people for the right program, right? I will assign the best people, the people who are getting most benefit to the skills development to skills development, right? So this is kind of for future is coming. But again, there will be very big pushback, because what you said is very important. Are we letting the machine to decide? Then there will be no people. Is it just we throw the data and then who's going to decide? The machine is going to decide? Then there will be a lot of ethics issues, right? Then we might be depriving some of the subgroups, right? For example, male are good in skills development. We are depriving the female. We are just assigning the male in the. So I don't know. This is be my response. I think I don't know whether I was able to answer your question.
Fantastic. But are you an economist as
Yes,
background?
I'm actually a student of Dhaka University Economics Department.
Okay, great.
Unfortunately, we did not met before. Probably you were not there. But I'm a classmate of Dean Islam.
Oh, good. Then my fear is, and if I can express it in that way, do you think we're going to be, as an economist or as economists, we're going to be redundant by these machines? Because
No,
all
I
they
hope
say, like,
not.
at the end of the day, say most models, they try to improve their predictability, right? Even if you are going for any kind of work, predictability is becoming a big issue. So if the machines, they can predict well, then basically, as economists, our functions become extremely limited. No? So survivability is at a stake.
No, it's a really, this is same question I also think, whether I will have job in future. Like even after 5 years, 10 years, what is the future? Even the AI, everyone is worried about AI. There are good part and the bad part of AI. We are talking about the AGI, artificial general intelligence, right? When the machine will be able to decide and we will not have any human intervention. In many jobs, they're predicting there will be, no people, only the machines. So, but I don't think very soon we're losing our job as an economist, because at the end, I think there will still need of someone in the back end, right? Even though machine do the things, we have to explain to the policymaker, okay, machine is telling us this, but why we are getting these results? We still have that scope of interpretation, right? And justifying, so to make people convince. I think still there is a role of economics, but I don't see this kind of causal machine learning as kind of a threat. But instead, this, as long as we can properly use it and explain, then this has a very good future. And the main thing I always highlight here is the heterogeneous treatment effect, which has a very, I mean, good future in terms of optimal targeting, right? So I want to make the best use of my resource. I want to make sure that everyone is assigned in the right program. So I see that direction. I still am hopeful that we can still survive as economists. Yeah.
Thank you so much for that, I would say, encouragement and the hope that you're giving in that. Yeah. Thank you.
Thank you, sir.
Thank you so much, Rajak sir, and thank you, Jamil, for your response. Any other question or comment? Any quick question? Okay, then we are already over time. Thank you so much, everyone, for joining our special lecture today. So our objective was to enhance the capacity of the young researcher, and since this is very emerging area of research, I hope people here and those who watch online will have a good starting point. If you are interested, I think uh, if you contact with Jamil, Dr. Jamil Said, he may help you further. Before I finish, let me request Yusuf sir, if you have any concluding remark.
No, thank you, Dean. Already 1 hour passed. I think it was a really interesting discussion. Hope we'll get further support from Dr. Jamil Said. Thank you so much. We are really grateful to you. Thank you.
Thank you, sir. Rajat sir, any comment?
No, I just wanted to thank Dr. Jamil Said. I believe we should be able to collaborate with you more so that we can learn well. And perhaps some of the things we can learn from you. So maybe from time to time, if you would come up with more bit of a practical or the work that you have implemented, those kind of a case analysis, that will be extremely helpful. Thank you so much for your
Thank you so much,
cooperation.
Rajat sir. And thank you, Jamil, for your very interesting presentation. And thank you, everyone. Have a good night. And I hope to see you in our next webinar. Thank you.
Thank you so much. Yeah, take care. Bye. Assalamu alaikum.